Okay, we are recording now. Summer's almost here, so things are looking up. I hope you are enjoying the weather. Those who are in Champagne, those who are in warmer places, great. Um, as usual, if you turn on your videos, much appreciated. Some logistics. There's a paper review out today. This will be the second last paper review, and after this, there'll be one more. But I hope you would enjoy reading this paper. Midterm is next Wednesday. Okay. I spent pretty much the whole weekend designing the next homework, which essentially is a preparation for your midterm. Okay, so the homework has questions from the beginning all the way to what we are going to cover next class. And all the homework problems is really what is going to prepare you well for the midterm. So please get started. The homework 3 would be released tonight. Okay, so that would be your best way of preparation. We'll talk a little bit about the midterm, what to expect, the format, etc. next class. Okay, the second half of next class. Okay. Finally, yeah, I hope you saw Liz's email about what is remaining in the rest of the course, and I think we are at we are at a good position. You're going to do an MP on HMMs and maybe another MP on dynamic time warping, or something related to speech or something related to sound acoustics. Okay, great. So today we are switching gears. We have actually switched gears, and we want to look at acoustics. And we started by looking at a little bit into optimization, very basics of optimization. By the way, folks, optimization is a great course to take. In Illinois, there's this course, ECE 490. And if you want to do machine learning, you want to do data science, you want to do many algorithms. If you look a random paper, you'll see there's some optimization, minimize this subject to that, maximize that subject to these. And the other good thing about optimization is it brings many mathematical topics that you've encountered before together. It glues them together, and that way it helps you also build your toolkit in other topics like linear algebra, like signal processing, like statistics, probability. It brings all of them together very nicely, and it's relatable because you know exactly what you're doing, right? Because you say, oh, this is what I need to maximize. This is what the constraints are. Okay, I really understand what's going on, right? I have a budget of money and I want to maximize my gain in the stock market. And this is what the probabilities of the stock variation looks like. Okay, I really know. You have an incentive to almost solve the problem because it kind of gives you things that you can use in your real life, right? And in some sense, this course is also kind of motivated by that you understand better when you really know what you're trying to do and you can see it right in front of you that way. Okay, so with that, are there any questions at this point about anything in the course, anything we've been doing in optimization before I get started? Nothing much. Okay, great. Okay, so let's get started. The goal for today, the plan for today's lecture is we are going to continue with a little bit more optimization, not much at all. By the way, I mean, the stuff that we are covering in optimization is probably 1/20th of what would get covered in an optimization course, right? We're kind of quickly looking at the basic ideas so that, remember, I always say, you should never have this feeling that, oh, this is so difficult, right? I want to always give you the courage to say, okay, I get what the area is trying to do. I have a sense of what is happening. So if you want to read up, you should be able to read up more. It shouldn't be that difficult, okay? So to quickly recap, optimization is all about finding extremum points. Extremums mean maximum or minimum. We've learned in high school that if you differentiate a function and you equate it to 0, that gives you the extremums. Actually, that's not necessarily true. That can also give you what are called stationary points, meaning here is a function which is a stationary point. This is not an extremum this is not a maximum or a minimum. But when you differentiate this function and you equate it to 0, you will get this point as one of the solutions of that equation, delta fx equals 0. Right? So then we said, okay, we get these extremum or stationary points by differentiating, but then how do we know what the whether it's a maximum or a minimum? And the answer to that lies in double differentiating it. But in high school, you always dealt with functions that are R to R, meaning that are in single dimensions, f of x, where x is one dimension. But in many real scenarios, like you're already seeing in this course, functions are vectors. The domain of the function is a vector, which essentially means, oh, the function has x1, x2. This is a vector x, which is x1, x2. And the function is a function of this vector x. And for each of those vector x's, you get a fx. Right? So fx goes from r square to r. And in that case, for that kind of a function, the way to double differentiate is what is called a Hessian matrix. You basically differentiate with x1 first, then we differentiate with the other x2, x3 to xn. Then you differentiate x2 and then again you differentiate with x1, x3, x4, xn, and so on. So this is the Hessian matrix. Okay. Someone mentioned Jacobian last class. This is not the Jacobian matrix. Jacobian matrix comes in when the function itself is vector valued, meaning you can have a function that is Rn to Rm. Okay, that is also possible, meaning the output of the function is not a scalar. The output of the function is also a vector. And then when you want to double differentiate that kind of a function, which is a vector valued function, this is a scalar valued function. Okay, that's when Jacobians come in. That's also useful and important in deeper optimization, but we are all worried about vector functions, but scalar valued vector functions. Okay, so now this Hessian it turns out that if this Hessian, this is a matrix, if this Hessian is positive definite, then it's a minima. If it's positive negative definite, then it's a maxima. And we talked about what positive definite means, right? That a matrix which is positive definite has all eigenvalues greater than 0. Another way of saying it, that any vector xt, if you take any vector x transpose ax will always be greater than 0. And we said, remember, this is a scalar. I hope you all see that this is a scalar. Right? You multiply a matrix with a column vector, that gives you a column vector. And then you multiply a row vector with a column vector. This is a row vector. You multiply that with a column vector, that gives you one value. Because that's a dot product. Okay. And positive semi-definite means that all the eigenvalues are greater than or equal to 0, as opposed to just greater than 0. And this also scales. Okay. And we said, look, if you say that the Hessian matrix is positive semi-definite, that's a necessary condition. Okay, let me say that again. The Hessian matrix at x star, right? The Hessian matrix is a function of that x, where x is on your vector dimensions, right? So for x star, if you plug x star into the Hessian matrix, in this matrix, if you plug x star, that will give you a real number matrix, right? It'll be a bunch of numbers in your matrix. And that you can calculate whether it's a positive definite or a positive semi-definite. If it is a positive semi-definite one, then it's a necessary but not sufficient condition. Okay, that means all minima maxima when you plug into the Hessian, it will satisfy greater than or equal to, it will satisfy positive semi-definiteness. But there could be other points that are not minima maxima that can also satisfy positive semi-definiteness. Okay, but we observe that when the function is, when the Hessian is positive definite, then it's definitely a minima. Or if the Hessian is positive negative definite, then it's definitely a maxima. Okay, so the sufficient condition is that the Hessian has to be positive definite. This is the sufficient condition. Okay, any questions thus far? Good. I'm hoping you are with me. And then we said, okay, very good. Positive definite, positive negative definite, all these give us, positive definite gives us minima, but that's like a local minima, right? For example, if you take this curve, if you differentiate that function and you equate it to 0, and then you check for positive definiteness, you will get these two values for both positive definite. The Hessian matrix will be positive definite, and the differential when equated to 0 will give you both these values, right? So clearly it's not the global minima. The question is, how do I get the global minima? Maybe I care about that, right? And the answer is, oh, if for a random function, it's very hard to find what is the global minima. Okay. But if the function is somehow convex, then local minima is the global minima. Okay, so then the question is, what is a convex function? And we said that the convex function is a function that has upward curvature. Hey, what does that mean? That's an English language. Yes, it's an upward curvature. It's like a bowl. It's an English language. Well, one more intuition is, if you take any 2 points on that bowl, the whole chord between those 2 points will always lie above the bowl. Okay, so okay, that is also intuitive, but give me a mathematical explanation. And the mathematical explanation is, you take a weighted average of fx1 and fx2. This is fx1, this is fx2 for this function. You take a weighted average of them, and how do you take a weighted average? You multiply it with alpha, and you multiply it with 1 minus alpha, where alpha is between 0 and 1, right? A basic average is alpha is 0.5. So 0.5 times fx1 plus 0.5 times fx2. That's the basic average of fx1 and fx2. That's in the middle, right? But if you make alpha is 0.1 and 1 minus alpha is 0.9, then you're like basically taking this point. So you can express any point over here by regulating alpha. Does that make sense? Right? Correct. Right? So this basically says the whole line connecting fx1 and fx2, because the whole line, any point on that line can be thought of as a weighted average of those 2 points. That must be greater than or equal to what? Oh, whatever weighted average that you've done, if I take the value of that function at that weighted average, this is the weighted average of x1 and x2, right? So if I take the weighted average of x1 and x2, which is this, the value of the function over there, that value is always less than the value on the chord. I hope this equation gives you peace. This equation, I hope, doesn't bother you. Very good. So then the question is, okay, now you've told me that if it's a convex function, and if I can find the minima, then that's the global minima, right? That's great, right? Because all I need to do is I need to check it's a convex function, equate the df dx to 0, and that's it. I don't even need to check for Hessian anymore. You agree? Because if you can test that it's a convex function, why do you have to check for Hessian? Very good. So then the question is, how do you test for convexity? And it turns out that the test for convexity is that the Hessian is positive semi-definite. Okay, very good. So then summary is, given fx, if the Hessian is positive semi-definite, then fx is a convex function. And if fx is a convex function, then grad of fx, differential of fx, gives me global minima. Make sense? This is the gradient of fx. And we said earlier, gradient of fx is basically a vector which says del f by del x1, del f by del x2, so on, del f by del xn, where f goes from Rn to R. That's clear? Good. So this basically gives you a vector. Okay, and that vector you equate to 0. That means you're equating that to a vector which has all these zeros, and that gives you all the values of x star. Guys, is that clear? Utkarsh, I see a little frown. Is that all right?
Oh, this is just my morning wake up frown.
You're not audible.
Oh.
Okay, maybe I'll do a very, very quick toy trivial most example, but hopefully this might be useful. Fx equals x1 square plus 3x2 square. Oh, hold on. I can hear him too. I'm fine, I can hear him too. Same here, I could hear him too. You could hear Utkarsh or you could hear me?
We could hear Utkarsh.
Oh, you could hear Utkarsh. Utkarsh, can you speak? I don't know. I didn't hear you at all.
Hello?
Oh, okay, good. Thanks. Right now it's
Yeah.
good.
Okay.
Thanks. Okay, so fx equals x1 square plus 3x2 square. What is del fx? Someone quickly? It's a vector.
2x1 and then 6x2.
You equate that to 0, which tells you right? Now, you could go ahead and compute the delta square fx, which is the Hessian, right? And then that will turn out to be a positive definite matrix, because this function essentially looks like a bowl. This is actually a convex function, right? And where does the convex function get minimized? Haha, at 0, 0. And that's the global minima. Okay, that's how you think about fx. Very good. Okay, so that's the global minima. But here is the bad news. The bad news is that even if fx is convex, in many cases it's difficult to solve for delta fx equals 0. And one example is over here, e to the power x plus x square. If you now do delta fx, this is, okay, first of all, maybe it's e to the power x1 plus x2 square. Actually, if this is a vector, e to the power x1 plus x2 square is not too bad, right? But the problem is, let's say this is e to the power x1 plus x2, or e to the power x1 x2, and this is x1 square times x2 square. Okay, then it is not easy to solve x1 and x2, or not easy to solve delta fx equals 0. Right? Because even if you differentiate, it is not, over here, it was nice that the differentiated value was only a function of x1 and only a function of x2. But in a complicated, in some complicated situation, this might be a function of x1, x2. This might be a function of x2 plus x1. And then you don't know how to solve it. Okay. So closed form solution is difficult, even if it is a convex function, right? And that is where we need to solve such functions iteratively. And this motivates what is popularly known as gradient descent methods. Okay, and that's where we are today. Okay, good. So what So what is gradient descent? Gradient descent essentially says, I need to start at some value x0, and then move from x0 to x1 to x2 all the way until I get to x star, where x star is the minima. That's my goal, right? I want to basically start at some random point x0. But because I want to find the minima of that function from that random point which gives me fx0 over here, I need to go in some direction which will take me to the fx star, where x star is the minima. Right? And in this case, this is x star. And this value is fx star. Right? By the way, guys, pre-notes are on the web page, and I uploaded a little late. So in case you haven't seen it, you still have time to download. Very good. So such that x star is the local global minima of fx. So what does this mean? If I denote this as xk, as a sequence xk, then what condition should hold? Fxk plus 1 should be what than xk?
Less than?
Less than xk. Right? I should find xk plus 1 such that fxk plus 1 is less than fxk. This is my requirement. And if I keep doing this, if I can satisfy this condition, and if I keep taking k to infinity, I will definitely find the local minima. Actually, in this case, the global minima, because it's convex. But for gradient descent, for that gradient descent algorithm, I don't even need a convex function. If it's a convex function, it'll give me the global minima. If it's a non-convex function, it'll give me a local minima. Right? Gradient descent doesn't have to be tied to convex functions. Are you with me? Right. Good. So from xk, we should go along a direction that decreases the value of fxk. Right? Imagine you're climbing down a mountain. Right? Imagine this, or imagine what can you climb down? Yeah, maybe there's a boat. Yeah, maybe imagine the boat that's lying bottom up. Right? This is a boat. And now from the top of the boat, you're climbing down. Actually, that also doesn't work. Fine. Just think that you're climbing down from this location. Right? And you want to basically, actually, maybe even if you're climbing down a mountain, right? You're standing on the mountain and you're seeing, your goal is to go down to the foot of the mountain. And you have many paths you can go towards. But you want to go towards a path that is definitely going to take you downwards the most. Right? That's the question you have at hand. Right? Which direction should I put my next step so that I go downwards the most? And not all directions are equal, because some direction might be a little flatter, some might be gradient. right? You have experienced this while you're climbing down a raggedy mountain. Right? So say this best direction in which I would go down maximally, let's call that direction V. That's a vector. Let's call it Vk, because at the kth step, the best direction in which I should go down is Vk. Okay, good. Let me erase this one. Yeah. Okay. So then, what is xk plus 1? Xk plus 1 is nothing but xk plus Vk. Make sense? I am over here, xk, right? I find the best direction to go downwards. And that direction happens to be this direction. Right? And if this is Vk and this is xk, then xk plus Vk gives me xk plus 1. Right? So it's a vector sum. But that Vk that I'm moving actually came from which direction I decided to go downwards while standing at that mountain. Very good. So the question is, what V direction will take us most downward? And answer is, this direction happens to be minus Fx. Okay, this is the beauty of it. If you're standing at xk and you look at that f of xk, the direction that will take you most downward happens to be minus of grad fxk, grad being the gradient. Okay, let's prove that. Okay, let's prove that why is it in the negative direction of the gradient at that point xk. Note that grad xk is basically this point. This is xk, this is fxk, and grad fxk is basically this direction. Okay, if you look at it this way, that will turn out to be in that direction. Actually, in this case, it will turn out to be in that direction. Okay, let's prove that. Okay, so Taylor's first order expansion, I don't know if you remember this, but just take it for now. You may not remember. Taylor's first order expansion says that Fy at some value y, again, y is like some point here. Y is some point here, x is some point here. Okay. So Taylor's expansion says Fy is nothing but Fx plus delta of Fx transpose y minus x plus some y minus x error term, some approximation, some other term which will approximate the rest of it. Okay. Fx plus delta Fx transpose y minus x. This is a vector, right? These are all vectors. Plus some error term. This is often called an error term. Okay. This is Taylor's expansion. In fact, you can even start writing more. You can start writing plus delta square Fx tau y minus x squared plus, you can keep doing. Remember, right? These are these series expansions that you've seen, but it's also possible to take all those later terms and put that in some term over here, which is going to be of the order y minus x. Absolute. Okay. Very good. Now, if I want to go in this case, if I want to go a little bit, let's say epsilon, then I can write y as xk plus epsilon v in the v direction. Okay, so let me write this y as xk plus epsilon v, right? And that will be equal to f of xk plus delta f of xk tau times, now what is y minus x? Y minus x is nothing but epsilon v plus order of epsilon. Agreed? Because y minus x is epsilon. Epsilon v, but it's order epsilon. Okay, or you can even write it epsilon v, that's fine. Okay, now I can basically, because epsilon is a constant, why don't I move the constant here and make that a dot product? Are you comfortable with that? Epsilon v is nothing but that v vector multiplied by epsilon, right? So I'm just taking the epsilon outside and then doing the dot product first. Okay, now look, I'm now going to bring fxk to the left side. So that means f of xk plus epsilon v minus f of xk. And this right side epsilon, I'm going to divide it here. And limit, take that limit of epsilon to 0. Okay, this becomes equal to delta of fxk t. Agreed? Okay. So rate of change of fx along direction v or vk. This is nothing but the rate of change of fx along the direction vk. Do you agree?
Professor, I just had a question concerning like the order of epsilon v, that term.
Right.
Is it because we're taking the limit going to 0 that we don't have to consider it right now, or do we end up considering it? I was just wondering like what we do with that term because it seems to disappear.
Oh, you take the epsilon from here, and in the limit, epsilon going to 0, this will go to 0.
Okay, got it.
Okay, so look, this physically means as you take an epsilon step towards the direction of v, how much, what is the rate of change of the fx value? Do you agree? In fact, this is your definition of differential almost, right? And that turns out to be this value. So if this value is large, or this, first of all, if this value is negative, that means you're going downward. If this value is positive, you're going upward, right? If this value is negative and large, that means you're going down a lot. Questions? Good. Okay. So then the question is, all we care about is this value. So what is the minimum value possible for delta fxk transpose vk? Isn't that what we care about? Because if we find what is the minimum value of this, then that minimum value will take me downwards the most. Right? So we care about the minimum value of this.
By minimum, just to clarify, you mean the largest, the
largest
negative
value.
Okay.
The largest negative value, yes. Okay. So now look, what is fx? What is fxk? That's a vector, right? This is a dot product, right? fxk is a vector, vk is a vector. So that's a dot product. So my question to you is, if fxk is a vector and v is a vector, when is this maximum and when is this minimum? Someone? This is maximum when? Even tell me in English.
When theta is equal to 90? Wait, sorry. It's a minimum when theta is equal to 90, right?
Is it? Adil, think.
Well,
Tell me when it's maximum. When is it maximum?
okay, so when you have two vectors and you take a dot product, if the cosine is equal to 90, then the dot product is equal to 0, right?
Correct.
So wouldn't the dot product being 0 here be when it's the minimum?
But why do you think 0 is the minimum? It could be negative too, right?
Oh, God. Oh, okay. So it would be when the dot product, okay, so when theta is equal to 180?
Correct. Right.
Okay, I don't know why I didn't think about the negatives at all.
Right. I mean, that's what also going back to Utkarsh's questions. Minimum means negative largest value. So if you make the v point in this direction, that's the smallest one. That's the minimum value. And when you make the v point in this direction, that's the largest dot product. Right? So max when aligned, that is theta equals 0. And minimum when opposite, that is when theta equals 180. Agree?
I kind of had a question. Could you go up a little bit when you looked at wrote the negative delta f xk?
Negative delta f x. Yeah, here.
Is that what you're alluding to here? Like the when theta is equal to 180?
No, wait. We started from a very basic expansion of fx.
Oh, I see. Okay, never mind.
And we said that, look, if I'm standing at x, we started with a basic definition of fx. Then we said, instead of y, which is some random point in that domain of x, right? I'm going to make that y xk plus epsilon v, right? So let's say, let me use blue. Let's take this one. Let's say this is x. And let's say this point is y. And this point is, oh no, actually, let me not take the minimum point as x. Let me take some other point as x. Okay. This point is x. This point is y. This point is fy. This point is fx. I took some random points. Taylor's expansion says fy, which is this point, equals fx, which is this point, plus delta fx transpose y minus x plus some order of y minus x. So what does that mean? It means if I take this fx and to that I add the gradient of fx, the gradient fx times y minus x, which is this y minus x. Okay. Plus some error term, then I will get fx. So in other words, if I take the gradient of f at x and to that I add, with that I multiply y minus x, it takes me upwards. Right? Because imagine like the gradient is like that, and to that I multiplied y minus x. That vector takes me like that. And I have to add some approximate error to take me exactly to fy. Okay. Adil, does that make sense? So we started from there, and from that basic equation which holds for any function, we kind of massaged that and we got to a point where we said, look, from fx, if you move epsilon in any v direction, then the rate of change is this. And then our question is, which v direction should we move so that the rate of change is negative, the largest negative value? Which means I need to find what is the largest negative value for this right-hand side.
Yeah, I sort of get it. I think I'll try to pick your brain on office hours.
Sure. Okay. So this is when it's max when it's aligned, it's min when it's opposite. And remember, guys, if we have vector A dot B, a dot product, that is nothing but L2 norm of A times L2 norm of B, or otherwise length of A times length of B cos theta. Okay? This is your basic dot product. Okay? So now tell me, this fx grad fxk transpose vk, what is it upper bounded by? What is the maximum value of this if I use the same equation here? This is fxk times vk. Right? Because cos theta is 1. That's the max cos theta can be. And what is it lower bounded by? Someone?
The negative version of that?
The negative version. Okay. So maximal downward direction is what? Is basically minus right? Because the direction in which you should go, right? It turns out the direction in which you should go should be this direction, right? In other words, Vk over here should go opposite of minus of fxk, should go in the direction opposite of grad of fxk. Right? Confusion? Nothing, right? So because now we figured out which way vk should point, should go down to make it the minimum. Very good. So this is minus fx, grad of fxk. So then we can write xk plus 1 equals xk plus vk, that we saw earlier, which is xk plus vk minus fxk, or let's write it this way. Right? This is called steepest gradient descent. Because this is nothing but xk minus grad of fxk vk. Okay, good. So steepest gradient descent, how should the algorithm work? The algorithm is as follows. Let's say k equals 0. That's your starting point. And pick some alpha, which is some positive value. Okay. And let's also pick some very small epsilon. We'll see how they become relevant. So now xk, pick xk as some random vector. Xk is x0 at this point. Pick some random vector, let's say this point. This is x0. Right? Now calculate delta or grad fx of k. Or I should write that as for that particular xk, calculate the function, basically differentiate the function and plug that value of x0 that you have picked, that random value of x0 that you've picked. That gives you grad of f of xk. Now, x of k plus 1 is x of k minus alpha right? We told you which direction to go, and that was the negative gradient direction. Right? Now the question is, how much do you go? Right? And that is basically defined by this term alpha. Ideally, you should go epsilon and then again calculate what is the new gradient, right? So imagine you're climbing down this mountain. At any point you say, what is the negative of this gradient direction? You take an epsilon step towards that, and again you compute, because after you take that epsilon step, the function could have changed, the mountain could have changed. So you need to find the new direction in which the gradient is taking you most downward, right? So you have to keep computing the gradient as you take epsilon steps, but that will take a huge amount of time. So there's a trade-off between, if you have a lot of time to wait, then you can make epsilon really small, so alpha really small. If you want to get quickly, you make alpha large, but there are some problems if you make alpha large. Okay. So then when do you stop? You stop when, if f of xk plus 1 minus f of xk is less than that epsilon value that you have chosen, right? Then terminate, right? Otherwise, k plus plus, go to line number 3. Right? So basically you're saying, I start with some x0, I compute gradient, and I go alpha along that gradient direction. So maybe that gradient direction is this way. So I go alpha, this is alpha. And this is my new xk. I say, okay, now from this point I compute the gradient. I go alpha. This is my new point. Again, I compute the gradient. I go alpha. This is my new point. Okay. Will you always get to the minima? Okay, okay, here are the questions that we want to talk about. Why does step size alpha need to be small?
Is it because you might overshoot the minimum?
You might overshoot. So one possibility is, if suppose you are over here and you compute alpha, at this point the gradient is almost flat, so you use alpha and you come over here. But so what? Now you're going to go back, no? So what's the problem if you overshoot? You're going to, because once you come from this point to this point, then at this point when you compute the gradient, you're again going to go back here. So then what's the problem?
If your step size is that large value, you're just going to keep rotating around the minima?
You can keep oscillating around the minima, right? Over here, you might have a large alpha, it will take you over here. Over here, you have a large alpha, it will take you over here, right? You might oscillate.
Can't you just choose like to use a smaller alpha when you get closer?
Yeah, but you do not know whether you've gotten closer.
You have no way to tell.
There is some way. There are optimizations on optimizations, right? You see the gradient, and you see if the gradient is becoming smaller and smaller, you make your alpha smaller. There are also other kinds of adaptive alpha called Armijo's rule, where you basically at every step you figure out what the best alpha is. There are possibilities.
So a larger alpha helps to get closer to the minimum, right? But it might not be able to get there. But a smaller one will, help you get closer, but it'll take longer.
Exactly.
Okay.
Now, here is the question I have. Can you see a case where you will get close to the minima and then you diverge? In other words, from x0, you get close to x, but then you go diverge. Can there be an alpha for which what Deep is saying is you get close to x star and then you oscillate around x star, right? You're oscillating around x star. That is not good, but still it's not too bad, right? Because you're in some neighborhood of x star, you're oscillating. But what is worse is you get close to x and then you again diverge. Is that possible?
Intuitively, that doesn't really make sense to me unless f of x wasn't convex. That would be like the only way that like.
Unless f of x is?
Not convex.
No, even in convex.
Maybe in a scenario where alpha is just the right value, such that f of x of k equals f of x of k plus 1, but you just overshot and went to the other side completely.
You swung from this side to this side, you're saying, Utkarsh?
Yeah, and then you
what?
hit your stopping condition.
No, but I'm saying, is it possible that you do this, then you do that, and then instead of coming this way, you go there, and then there, and then there, and then there, and you keep diverging? Okay, here is the intuition. Remember, alpha is getting multiplied by f of xk, right? So as you get close to the x star, your alpha is getting multiplied by a smaller value, right? But suppose you've chosen a large alpha, right? And suppose you're over here. You've gotten close to x star. But now because you are multiplying alpha by a larger value, you move to this point. So now, at this point, you had alpha and you were multiplying with a smaller fxk, right? Because the gradient of this point is smaller than the gradient of this point. Do you agree? So when you go from here to here, here you get multiplied with a larger value of fxk. So you go here. Here you get multiplied by a larger, even larger value of fxk because the gradient is increasing as you go along this direction. Right? So the intuition is, it's not only alpha, it's also the f of xk which matters. If f of xk is large, then with that alpha you might jump backwards. And if you jump backwards and you get to a point where there's even a larger f of xk, then you might again jump backwards. Utkarsh, you have a
Were we not using delta f of xk only for the direction? Or does like the magnitude of that matter as well now?
Oh, but look at this case, right? You're multiplying alpha with f of xk. F of xk is a vector, right? So the magnitude would matter. Right? The direction is opposite of f of xk. But how much are you going down in that direction? Minus f of xk, the actual magnitude of that vector. Right? So with larger alphas, there's this risk that if you overshoot and you get to a point after overshooting where the f of xk is large. For example, imagine this function was like this. Right? Maybe I should draw that. Imagine the function to be like that. That is also convex. Right? But now from here, you overshoot, and based on your alpha, because this is x, right? You overshoot and you come here. This is your alpha. This is your alpha. Now you get here. Here, the f of xk is very large. So then from this point, which is xk plus 1, you take f of xk, which is very large, or f of xk plus 1, which is very large, and multiply that by alpha, you shoot back here. There, that function is even larger. That gradient is even larger. Right? So from here, you shoot back here. Here, you shoot back there, and you've now diverged. Okay? So this is why it's important to choose small alphas, but not too small that you will be super delayed.
You know, do you not run into that problem if f of x is symmetric?
No, you don't. You still can run into that problem, right?
How would you run into that problem if it's symmetric?
Oh, because if it is symmetric, you're right. If it's symmetric, you can oscillate from this side to this side.
Okay.
Wait, let me think. No. You can still run into that problem, Adil. Suppose you're here, okay? And alpha takes you here, okay? Now, the question is, are you going to go above this point or below this point? Okay, I need to think about that, okay? I'm not sure. Let me think about that and tell you if it is symmetric, it'll oscillate, it can oscillate for sure. Can it diverge if it is symmetric? Okay, let me think about that. Okay, and one more thing I want you to think about is, does SGD take the shortest path from x0 to x star?
Just to add to that question.
Yeah.
Just as like a side note, f of x is going to be like the problem, right? Like you can't really control for the symmetricity or whatever, right?
Correct. Exactly.
Okay.
F of x is the problem that's given to you.
Okay.
Right? This f of x is basically saying, if you buy this much of Apple stock and this much of Google stock, what is your likely return? This f of x is your likely return. Right? That's what f of x is. Right? Very good. Okay. So that's all we are going to talk about. And I want you to think about this question. Does steepest gradient descent take the shortest path from x0 to xk? Meaning, does it take from x0, does it start and does it come to x star like this? Okay. Something for you to think about at home. Okay. If any questions thus far? Oh, we are running late. Oops. Okay, if not, I want to move into acoustics now. And many of the things that we've talked about in the past, channel, convolution, multipath, line of sight path, Fourier transforms, all of those things would apply in acoustics as well. Okay? All of those things would apply. The only difference in acoustics or rather the main difference in acoustics and wireless or RF is that, remember when we talked about FFTs, we said this is the frequency band This is frequency 0 and going all the way till F. For a thing like Wi-Fi signals are transmitted at some frequency called the carrier frequency. Right? And Wi-Fi would be some 20 megahertz around the carrier frequency, and that would be the bandwidth, 20 megahertz. But this carrier frequency would be 2.4 gigahertz. Guys, did we talk about this? Oh, maybe not really, or maybe it doesn't matter too much. All I'm trying to say is everything that we talked about in FFTs, we said that, look, this is the bandwidth of the signal, right? This is B, this is minus B. That we talked about, right? We said, look, bandwidth is symmetric around Fs by 2. So we can think of this as minus Fs by 2 to Fs by 2. Right? I hope you remember that one. Right? So if you think of Wi-Fi transmits on a 20 megahertz bandwidth. So that means that Wi-Fi is like that, 0 to 20 megahertz. So instead of that, you can think of it as this is Wi-Fi. Okay. Cops use another band. Cops use police cars use a different channel to talk to themselves, right? You just cannot listen to them. I mean, you can buy some certain devices and you can start listening to them, but you're not supposed to, right? And that is, let's say, that is 2 megahertz. So they have a band that is 2 megahertz. This is 1, this is minus 1. Airplanes talk on some channel that is another band, which is, let's say, 10 megahertz. So that is like 5 minus 5. This is airplanes. So everyone wants wireless channel. But then if Wi-Fi and police cars talked simultaneously, then that would be a collision, right? Because on the same frequency band, Wi-Fi, you will transmit your YouTube video and police cars will transmit their walkie-talkie or whatever their coordination signals. That will be a mess. So what happens in real life is you shift these bandwidths to higher frequencies. So basically, you move Wi-Fi to some other frequency called the center frequency, which is at 2.4 gigahertz, and you have 20 megahertz around that 2.4 gigahertz. Police has 2 megahertz, so they might have a different center frequency somewhere here, and they'll have a 2 megahertz police. Airplanes might have some other center frequency here, and they will have 10 megahertz here. Cellular towers, Verizon will have its own frequency. Vodafone or Sprint and AT&T, they'll have all of these, their own frequencies, and they'll have their own bandwidth around those frequencies. Okay. So your Wi-Fi router actually transmits this signal. Your laptop receives that signal and moves this 20 megahertz thing around 0. This is called baseband. Right? The only reason to send this signal around this frequency is because I don't want to collide with other people. But once I've received the signal, I bring it down to 0. High-level intuition, I just want to give you a sense. Now, the only difference with acoustics is that there is no notion of carrier frequency. Everything happens in baseband. Okay, so acoustic signals are actually much lower bandwidth. It goes from 20 kilohertz, 10 kilohertz to minus 10 kilohertz. That's the bandwidth is 20 kilohertz. That's the main difference with acoustics. You don't have to know that, but just as a matter of fact. Very good. So what we want to talk about is, in acoustics, one of the interesting applications that a lot of people care about in mobile computing is noise cancellation. Okay. So we want to talk about noise cancellation and what happens inside it. And then we'll talk about how IoT and mobile computing can actually help with this classical area of noise cancellation. Okay. So today's goal is to kind of look into what's inside a headphone. Okay. And if you break open the headphone, what you would see is the following mainly. There is what is called a reference microphone. Okay, by the way, what is noise cancellation? Someone? Quickly in English. What does a noise cancellation headphone do?
It removes background noise, so all you hear is what's coming from your speakers.
Okay, very good. So one way to think of noise cancellation is that someone is talking, that sound is coming to your ears. That sound is also coming to the headphone. And the headphone needs to do something to that noise and play what is called an anti-noise. Right? So the headphone should play this anti-noise. And this is noise, such that at your eardrum, the noise and anti-noise destructively cancel each other. That's the goal. That's the goal of noise cancellation. Okay, very good. So what does the earphone contain? The earphone basically contains the following. It contains a reference microphone, a DSP chip, a digital signal processor chip, an anti-noise speaker, and something else that is called a feedback microphone. There are two microphones. One is on the inner side of the ear towards the inside of the headphone, and another that is towards the outside of the headphone. And let's try to understand what goes on in noise cancellation. So let's say someone is talking at the corridor, and let's call that signal X. That signal is a vector, so X is a vector. Okay. That signal arrives to your headphone or to the reference microphone. That's the outer side of your headphone, but also arrives towards your ears. Note that because the headphone has some width, the signal that arrives into your ears and the signal that arrives at your outer part of the headphone, they're not the exact same signal, because with all the multipath and everything, the alignment of the phases of those echoes and multipath is different at this location and at this location. Are you with me? Very good. Even though this is like a 1-inch gap. Very good. So what does your headphone do? Your headphone takes this signal from the reference microphone and gives that signal to the DSP. Let's say that signal is S. And the DSP does some computation, changes that signal, because the DSP's goal is to somehow cancel this sound that is arriving into the ear. Let's call that signal D for desired signal that you want to cancel. So the DSP wants to generate the negative of D. Okay, so the DSP comes up, takes S as input and tries to generate the negative of D. We don't know if it can, but it generates some signal and it gives it to a speaker. This is called the anti-noise speaker, and that speaker plays that sound, whatever the DSP gave the speaker. Now the DSP doesn't know whether it has done a good job by producing a signal that is canceling at the user's eardrum. It doesn't know that. So how will the DSP do anything to kind of get better? How does the DSP know that it has succeeded? So that is why there is this other earphone over here, which is as close to the ear as possible. This is called the feedback microphone. And the feedback microphone says, hey, I am getting D and some other signal that the DSP has produced, right? Let's call that Z. And I am essentially getting the sum of D and Z. If the DSP did a good job, what would the feedback microphone hear?
Zero.
Zero. If the DSP did a great job, the feedback microphone would hear zero. If the feedback microphone is hearing some signal, the DSP is not doing a good job. Therefore, the feedback microphone tells the DSP, this is what I am hearing, you better up your game. Okay? So this is what is essentially going on in a noise cancellation headphone. Okay? So we want to achieve noise cancellation at the feedback microphone. So we want signal D minus the signal output of DSP to be equal to 0. You agree? Which means the DSP needs to somehow distort the signal S. And any distortion or any modification to that signal S, I can represent as a filter. Okay? So filter means what? I'm going to basically multiply. I'm going to do a dot. I'm going to basically multiply every value of that signal sample with some weights. And that's what I'm going to do. Okay? So DSP needs to convolve. Oops. DSP needs to convolve S with a filter W, okay, such that dk is the kth sample of D minus WTS equals EK, which is almost equal to 0. What is WTS? Let's just quickly write it. W is a weight vector Oh, actually, maybe it will become clearer once we go here. Okay? So WTS is basically a dot product. It's a weighted average of all the signals samples that I'm getting. It will become clear soon if it's not clear to you. Okay? And this is the, sorry, what is EK, guys?
Is that your tolerance, like how close to 0 you can get, or?
Yeah, that's true. But who is measuring EK?
The feedback mic?
The feedback microphone is measuring EK, right? And you want the feedback microphone to measure 0. Okay. So we can model this as the following. DK is coming, and with that, I basically take SK and I delay the signal and I multiply, sorry. Yeah. This is a delay, okay? So now tell me, at the current instant, SK is coming in. What is coming out through this wire? W1 is a multiplication to SK. So what is coming out through this wire is W1 times SK. Do you agree? Very good. What is coming out through this wire? When the signal SK is over here, what signal is over here? The previous signal, right? Because you're delaying it. You see that? So what is coming out through this wire? Someone?
Is it W2 SK minus 1?
Very good. W2 SK minus 1. This is WN SK minus n minus 1. Does that make sense? So then I can write so then this output of this addition is nothing but W1, W2, so on, Wn times, tell me what is this vector? Sk, Sk minus 1, so on, Sk minus n minus 1. Where have you seen this? You remember when the channel, when we were looking at the channel and the signal, we were flipping the signal and we were moving it into the channel. This is convolution. Okay. This is basically this weights convolved with the signal. And as the signal comes in, this signal is like a moving wind. This is like a sliding window on top of the signal that is coming in. So the DSP's goal, which is the DSP? The DSP is basically this. That's the DSP. So the DSP's goal is to find that W vector, right? Which W vector should I multiply with the coming values of the signal so that subtracted from the signal that's going directly to the feedback microphone gives me 0. That's the goal. Okay, and you have to do it pretty fast, right? Because the signal is, the acoustic sound is coming and hitting your ear. You're basically trying to generate the opposite of that, D sound. Okay. So for noise cancellation, D is basically X convolved with some H. Basically, H is the channel over here. Here is the channel. Right? What does H means? H means it's a multipath channel. There are all kinds of reflections that are coming together. And S is also the same X that's coming out of the person's mouth who's talking on the corridor, convolved with some other channel G, where the G channel is this G. And that channel is, this is the line of sight, this is the multipath, there are other multipaths, all of those coming together. Plus noise. Guys, is this clear? So now we want W when multiplied or when convolved with S, this is convolution. So when W is convolved with S, we want it to be negative D. So then look, W has to be minus G inverse convolved with H. Tell me if that is right. Why? Well, because I want W convolved with S to be equal to minus D, which is equal to minus X convolved with H. I'm just ignoring noise for now. Right? And S is X convolved with G. So W is nothing but minus G inverse convolved with H. Is that clear, guys? And another way to think about it is, let's convolve S with W. By the way, W convolved with S is the same as S convolved with W. There's no difference. So let's convolve S with W, which is nothing but S is X convolved with G convolved with W, which is nothing but X convolved with G convolved with W is minus G inverse convolved with H, which is this G inverse cancels. So that is X convolved with H. And what is that? Negative. Right? And what is this, guys? Minus X convolved with H. Look at this.
D.
Minus D.
Minus D.
Yeah.
Minus D. Right? So this is minus D. We've achieved what we wanted, right? So essentially W is trying to estimate this. This is where gradient descent will come useful. Right? W will keep trying to change. Imagine, so one way to think about it, this is, I have a function whose domain is W1, W2, so on till Wn. Right? And my function fx or fw is basically dk minus wts. That's the function I have. Right? In fact, that function might have a 0. I want to find the w that will bring me to that minimum value. Right? You see how noise cancellation is now getting connected to things we exactly talked about. This is exactly an optimization problem. Right? The question is, how do you compute w? And there the answer is, oh, we are going to rely on optimization. I want to quickly do this. So we will try to minimize. Ideally, we should have minimized EK. But for many reasons, we are going to minimize expectation of EK squared. Okay? This is often called minimum mean square error. Okay? Squaring has some value that everything becomes positive. Okay? And we don't want to minimize one instance. We want to minimize this on average. Right? Minimizing one instance is hard, right? Because you have to change everything, right? You want this thing to be averaged over a number of samples. So you want to basically minimize expectation of EK square. Okay? Essentially, you want to find some W star over here in the domain of that function, right? And you don't know where the W star is. So you start from some point and you try to come to this W star point. Fantastic. So now let's write out the equations. EK is dk minus WT sk. You agree? So EK square is expectation of dk minus WT sk times WT sk transpose. Okay. So now, you know, right, A plus B transpose is nothing but A transpose plus B transpose. Also, AB transpose is B transpose A transpose. Okay. So then we can write this as expectation of dk minus WTSK times dk transpose minus sk transpose WT W. Okay. Good. Now let's multiply inside the bracket, inside the expectation. dk square. dk transpose is dk square. So that's what we have. Okay. Now, WTSK and W transpose SK and SK transpose W, what does that become? Anyone? that becomes, oops, WT SK transpose W. SK transpose is covariance. Okay, so that becomes W transpose RS W. This is covariance. Okay, next, this and this, which is minus W transpose RSD. It's the signal that you're getting at the headphone and the signal that's arriving at your feedback microphone. It's the covariance of that. Hey guys, I have two random variables X and Y. What is E of X and Y? Right? That's that matrix over here. Hey, remember there are two random variables X, Y, right? You think of it as two vectors. E of X, X equals ABCD, or X equals 1, 2, 3, 4, Y equals 1, 2, 3, 4. How do you think of that? You make it a two-dimensional matrix, right? Go back to probability. Whenever you have confusion, think of a random variable as a vector, right? And there are X and Y, X, Y. So you make them a two-dimensional matrix. That's the covariance matrix. Very good. And then we have, so we're done with this one. And now we are done. We need this one times this one, which is minus, oh, again, it's basically RSDW. Right? Because this one, oops, this one times this one, again, SKT DK, the expectation of that gives me RSD, and W is the weight matrix.
Would RSD not be transposed here?
Oh, remember that A transpose B is the same as B transpose A. Why? A, this is, let's say this is vector A, transpose B, right? Is like A's first element multiplied with B's first element, A's second element multiplied with B's second element, A's last element multiplied with B's last element. This is the same as B transpose A. Right? So that doesn't matter. Okay, good. Now to minimize this function is basically Rn to R. Right? You see, right? This is the function that we need to minimize. Sorry, this is the function we need to minimize, which is we want to minimize this whole function. But this function is a function of what is the domain of that function? W, this. Right? This function FW is basically this. Right? So the domain of the function is W. So now then what do we need to do to come up with the minima? The first step we always do is delta F. With what should we differentiate? With respect to which variable should we differentiate?
W.
W equals 0. Right? This we can do because this essentially means I need to differentiate this with respect to D, with respect to W. Okay, guys, quickly tell me what is this? How do you differentiate? What is the differential of this with respect to W?
0.
0. Perfect. Plus, what is the differential of this with respect to W?
2RSW.
2RSW. Very good. 2RSW minus, these two are the same. Okay, so differentiate both of them, this one and this one. Utkarsh?
Minus 2RSD.
Perfect. equals 0. Okay. So then what do you have? 2RSW equals 2RDS or RSD. Therefore, what is W star? W star is RS inverse RDS. What does that mean? This means the W star is you take the covariance matrix of the source signal, or sorry, you take the covariance matrix of the signal that is received at the outer earphone of your noise canceller, and you take the covariance between the signal that you received at the outer earphone and the feedback at the outer microphone and the feedback microphone. RS is the covariance matrix of this signal. RSD is the covariance matrix between this signal and this signal. The problem is, what is the problem, guys? Can you do this? Can you actually find W? Do you know D? Do you even know RS? Okay, we'll get to that. Okay. As I will say very soon, you do not know this covariance matrix. Right? The sound is coming. How do I know that covariance? Right? How do I know what is coming after this? How do they co-vary? Right? I get a signal sample. I get that the next sample is coming. How do I know whether the next sample and this sample, they go up or go down together, or they go up and down in opposite ways? I don't know that. What is covariance? Covariance means, do two things go up and down at the same time, or do they go up and down in different ways, right? That's what covariance means. Very good. So we'll worry about that later. But now let's first figure out, is this a minima? Right? And then we have to say delta square F is what? If this is delta F, what is delta square F, Utkarsh?
2RS.
2RS. So now we have to say, if that covariance of the source signal, if that is positive definite, that is RS is positive definite. Guys, I hope you've observed by now, this is not a greater than sign. This is a curly greater than, and that means positive definite, right? Greater than is straight. This is a curly greater than. So if this matrix is positive definite, then W star is a minima. But who knows what this matrix looks like? I don't know, because the signal has not yet arrived to me. Okay. Now, this, we did not do gradient descent for this one. We just directly solved it. You can also do gradient descent on this one, and you'll actually arrive at the same solution. Right? It will again turn out to be W is RS inverse RDS. And when I put out the notes, you'll see the derivation when you do gradient descent. There it will be, just to give you the first step, WK is going to be WK minus 1 minus alpha W f of WK. Sorry, f of WK minus 1. So this is our gradient descent equation. You remember? And you know what is this, because you know what the gradient of f is, right? So you can plug things and you can keep doing it. I'll put in the notes. I want to skip this quickly because this was just a side note, that even if you do gradient descent, W, when k goes to infinity, this W infinity is going to become RS inverse RDS, which is same as above, right? But the only advantage of gradient descent over here is that you don't need to invert the RS matrix. If you do this way, like a closed form solution, you need to find what is RS inverse. First of all, we don't know what is RS, right? But I'm assuming even if someone told you that, oh, this is a sound that is coming from the airplane's engine. Yeah, maybe in that kind of a case, you know RS, right? You know that the sound that comes from the Boeing 737's engine, you've heard that sound before, and you know that the covariance of that sound, you already know. Then you can cancel even with a closed form solution. But even then, you have to invert this matrix, right? With gradient descent, you don't have to invert because you're going to converge on that W by going one step at a time. Okay, here's the big problem, is that RS and RDS are both unknown. Because this is the covariance of the source signal, and this is the covariance between the signal that's arriving at the eardrum and the signal that's arriving at the reference microphone. Okay. So here is the core idea, and we'll stop here. Approximate the RS and RDS with the current value of SK and DK. So in other words, given that we have differential of F as 2 RSW minus 2 RDS, we are going to approximate that as 2 SK transpose times W minus 2 SK DK. It's an approximation for sure. This is an expectation. This is an expectation. But since I do not know that, I'm just substituting that with the current value. This is like saying that I should give you a job, or Google should give you a job based on your expected GPA, which is an average of all the GPAs that you have, grades that you've had across all the courses that you've taken in undergrad. But Google doesn't have that luxury. So Google says, whatever grade I get in this semester, I'm going to use that as an approximation. So if you've done well, you'll do well in this semester as well. Right? It's an approximation. Okay. So you take that approximation and that approximation for your gradient. Now look, this becomes, you take SK out. You take 2 SK out. What you have is SKT W minus DK. What is this?
Is that what we're measuring from the kind of feedback microphone?
Correct. This is SKTW minus DK is exactly right. So this becomes minus 2 SK EK. Haha, that's the best part now. EK is what I can measure, SK is what I can measure, and I have approximated that gradient with the current values that I can measure. I'm going to now do gradient descent. Right? Observe that I do not know this function. I do not know that function, but that gradient of the function, by some approximation, I'm able to measure. And for gradient descent, all I care about is the gradient of that function. Okay? So next time we'll start from here, where we'll take the gradient of the function and we'll do gradient descent on that. And we'll say, oh, this is exactly what noise cancellation is doing. Okay? I know I took a little long, quite long today, but I couldn't have finished this without this logical end. Okay, class ends over here. If you have questions, stay back. Otherwise, I'll see you on Wednesday.
Thank you.
Thanks, guys.
Thank you.
Thanks.
Hey, Professor.
Hi, yeah.
Can you go back to the steepest gradient descent slide? Not the slide, sorry, the notes. Yeah, this one.
Yeah.
The next one, actually. Yeah. So yeah, these steps. Can you explain the termination step again? I'm unable to like wrap my head around why it terminates when it's less than epsilon, like step number 5.
Sure. So the point is this, okay? I'm trying to find the right place to draw. Let's look at once you get close. Sorry. Once you get close to the minima, right? If I zoom in with a very strong lens at this location, it is going to look like this, right? So now, at some point, I've come to this xk, right? And what is the gradient? The gradient is this. So the gradient is almost close to 0, right?
Mm-hmm.
So now when you multiply alpha times gradient, whatever alpha is, because this gradient is very small, xk plus 1 is going to be very close to xk. Because remember, xk plus 1 equals xk minus alpha xk, alpha gradient of fxk. This is very small once you get close to the minima. Which means this is very small, right? Which means what you're taking away from xk is very small, which means xk plus 1 is very close to xk. Right? So you move from xk a little bit xk plus 1. Now at xk plus 1, the gradient becomes even smaller. Right? Because the gradient is going towards 0, right? At the minima, this point, the gradient will be 0. Because it's a flat line at that minima. So as you go towards it, your gradient of xk is going smaller and smaller and getting closer to 0. So the way you're going to advance towards that minimum x star, right? Let's say this is the minimum. So the rate at which you're going to advance towards that x star becomes smaller and smaller, because at every point, the next jump you will have is a function of this gradient of fxk, and the gradient of fxk is almost 0. Right? So you go from xk to xk plus 1, then you go smaller. So you have to go really epsilon you have to wait a lot of time before it progresses to x star. Right? Before the gradient really becomes 0. So you said, look, I'm not going to wait for that long. Okay. So what I'm going to say is, when I'm moving from xk to xk plus 1, if my function is not changing by more than an epsilon, and that epsilon could be a very small value, then I'm going to say I'm close enough to the minima. Right? And the hope is that your function is not changing much, because you're so close to this x star that the gradient of the function has almost become flat. right? If let's say the function goes up like this, right? If you are at this xk, then along that gradient direction, you're going to drop a lot. So then fxk minus fxk plus 1 minus fxk would be a large value because you dropped a lot. But once you're close to the minima, because that gradient is very small, it's almost close to 0, you're not going to drop too much anymore. You're just dropping tiny amounts at every step. And if you wait for long enough, yes, you can go. But if you're dropping that tiny amount for every step, then you can tell yourself, hey, I'm pretty close to the minimum value and I'll stop. I'm not going to waste my time for a marginal, very small return of investment. Okay.
Got it. Yeah. Yeah. This makes sense. This was super helpful.
Good.
Thank you.
Sounds good. Yeah. Yeah. I think thinking about this is valuable. I think these are things that, the more you kind of swirl this in your head, the more you kind of chew on it, it becomes clearer and clearer.
If I could interject real quick about
Yes,
that
yes.
same question, how do you decide what epsilon is? Is this something that like a developer decides, or?
Exactly. The developer decides. Yeah. It's a function of how much do you care about, or what is the penalty of being far away from the minima, right?
Okay. I guess I had other questions about the rest of your lecture. When you were calculating
recording, because otherwise the recording length becomes super large, and also the office hour is separate. So
Okay.
I'll stop the recording and then we can discuss questions.